Welcome back, contestants. I'm your host, Mr. Mulholland, and on this episode of Chemistry, we're going to be taking a look at how we can use density to find the purity of a substance. Let's get started. So, once we have a set of solutions, we are actually able to figure out how pure those substances are. And before we get to that right away, let's explore or take a look at some types or brands of water bottles that you might be drinking. Now, some of them can kind of be advertising different things. You have some Mountain Springs that say they take it directly from river water, or that maybe they're advertising that it has beneficial minerals, or others that are saying that it's pure water and there's no minerals or no extra things in there. How can you tell? Well, part of today is finding out or determining substances that can be found in solutions. So we're going to take a look at some water substances, and we're going to see how exactly that might work. Okay, and so we're going to see what that might look like too here. So say we have three samples of water here, each weighing different grams here, 100, 103, and 114. They all have 300 milliliters in each sample. So how do we figure out, if we had to guess which one is the most pure water substance, which one do you think that would be? Well, it's probably important to know that the density of water is 1 gram per milliliter. So if we had 100 milliliters in a beaker of pure water, it would be 100 grams. Right? So that means probably that substance on the left, or this beaker on the left, is probably the most pure of the three just by looking at the weight. We would have to figure out or try to perform some more reactions if we wanted to really make sure that was correct. But that is a very good sign to start that, 100 grams, that matches up with the density of water, so the two would be the same. When you have 103 here and 114 on the right, that's getting into more minerals or substances that are unknown. Okay, so how can we figure out those substances, or how can we figure out how many substances are found in water? Okay, that's kind of the goal for today. So let's take another example. We have 3 beakers, and they all weigh different masses, 103, 104, and 119. And we put different substances into each one. Okay, so sodium chloride in the far left one, and different concentrations of sodium chloride in each one. So we can kind of see molecularly what's happening in each of them, here, here, and here. And we want to pay attention to the ball floating in the water, right? Because the ball floating on the left is halfway sunken, right? There's not a lot above water. Here, it's risen more, and here, the ball is almost completely on the top. And that has to deal with density, right? Because if we look at the concentrations of the three, the one on the right, 5.1 molarity of sodium chloride, that means it's the most dense, right? Molarity is all about concentration per volume of solution. So here we literally have more molecules per liter of solution. And that's going to cause the ball to float more, right? Because as there's more concentration, there are more units of sodium chloride. Okay, so the higher the salt concentration, the denser the solution will become. And if we think about some real life examples of that, we'll take a look at the Dead Sea. Right, so this is the Dead Sea. It is the highest salinity body of water. It had about 35 parts per mil, which just basically means there's a lot of salt in there. And so you can actually go to the Dead Sea and you can lay down very kind of comfortably, almost like you're sitting down while you're there. So you can read the newspaper or do a TikTok or whatever things you normally couldn't do in the water. All right, so with that in mind, we're going to take a look at some more solutions where we have the same mass but different solutes. right? So different things being put into the beaker. All right, so imagine that you add 10 grams of 3 different solids to 3 different beakers, right? 10 grams in each one. The substances of the 3, though, are going to be different. So we have copper sulfate in the first one, sodium hydroxide in the second one, and potassium chloride in the third. So they all have the same approximate mass, but do they all have the same concentration? Well, let's take a look at a few things. One, let's take a look at the molecular diagrams of each one here, here, and here. And we can see that sodium hydroxide has a lot of molecules per liter of solution. Okay, so we'll explore kind of why that is here in a second. What I really want you to focus on now is this table of the molar masses, right? Because we have 3 beakers, 3 different substances, and the molar mass of each of those substances can be found at this table. Which one has the highest amount? That's copper sulfate at basically 250 grams per mole. Next one is potassium chloride, and then the smallest amount is sodium hydroxide. So what that means is, again, molar mass. If you have a gram or if you have a mole of that substance, you will have, in copper sulfate's instance, 250 grams. Right? So 1 mole of copper sulfate is heavier than the other 2 by quite a bit. Which means that if we needed 10 grams of each one, copper sulfate, we don't need that many of them, right? We need very few amounts of copper sulfate. Potassium chloride, we would need more of, right? Because it weighs less, so we just need more molecules in the solution. And finally, sodium hydroxide, that weighs the least. So to get to 10 grams of sodium hydroxide means we have to put a bit more, or quite a bit more of molecules or moles in there. So if we have more moles in there and the solution or the volume is the same between each substance, then the concentration for sodium hydroxide is going to be the greatest. Right? So no, they don't all have the concentration. What determines concentration? Remember, this is molarity, so we're talking about moles over liters. So if there's less moles per gram, then the concentration is going to be less. If there's more moles per gram, say for like sodium hydroxide, then it's going to be higher in amount and higher in concentration. So what determines mass? That's the molarity as well as the molar mass. Right, because we're looking at the amount of substance, and then we're also looking at how much that substance compares to a mole, or how much that weighs, how many, like 1 mole of copper sulfate, how much does that actually weigh? All right, so basically the lower the molar mass means the higher the concentration needed to get to 110 grams, right, to get to what the other ones are equal to.